There are two mathematicians who've set themselves the task of figuring out how far up the top of the clock on Woodburn Tower is. They're teaching trigonometry, so there's some trig information that might be relevant. We could measure to the very top, that ventilator on the top, or to that little finial. We're going to actually measure to the top of the clock tower. Could do it to the bottom. Could do it to one of the architectural features somewhere up or down the tower. But what we have available is information about how angles and triangles work, and we hope that'll be enough to figure out how tall the tower is. The tower is. If the measurement is going to involve trigonometry, it's going to have angles in it, and so we're going to measure in terms of using a transit that we borrowed from the civil engineering department. The way a transit works is that the base is set up level with the bottom. There's a bubble there that Professor Miller is adjusting to make it absolutely flat. Then the telescope has a crosshair in it that you set at an angle to sight on something. Here's what it looks like up close. When we measure, the telescope is adjusted so that the angle is measured based relative to the horizontal. It's called the angle of elevation. And that's the setting, that's what's happening now. This is Professor Mays measuring to the top of the clock face. Clock face. There's what the transit looks like. A little closer, you can see the telescope and the eyepiece on the right. That wheel has at the bottom a dial that's lined up against another dial. They're both calibrated in degrees. When it is set up so that the transit is flat, horizontal, then the degrees is set up so that it's 0 showing on the bottom dial, and the telescope being horizontal has a 0 lined up against it on the top dial. Here it is closer to it on the top dial. And you can see that first angle measure is set up so that the 0 on the bottom has a horizontal and an angle. The inclination that the telescope makes with that looks like 22.5 degrees, maybe a hair over 22.5 degrees. Well, you will use 22.5 in our calculations. That's the angle of elevation of that first angle measure. Now, if we have only right triangle trigonometry to use, here's what we might try to draw. In Woodburn Circle, what we'd like to find is the distance from the ground up to the top of the clock dial. And to build a triangle there, the transit is set up at the base of those bushes in the front of the picture, at the front of Woodburn Circle. So that distance is the distance in. That could be one side of the triangle. The perpendicular distance up the tower could be another side. And the hypotenuse would give the third side. And the angle that we measured was between the hypotenuse and that ground leg. That's what we found to be 22.5 degrees. Now, the problem with using just that information to find the height of the tower is that we don't know enough. Two things. One is a problem in doing the measurement. In fact, the way Woodburn Tower is constructed, that clock dial is set in a little bit at the top, so that the perpendicular, when we drop it, won't come and land all the way outside the building. It's going to be in that lobby area and a little bit hard to get to. Another problem is that distance along the ground isn't something that we have an easy measure for. I guess we could pace it off, but that wouldn't be very accurate. We went up to do this measurement with a 25-foot tape measure. So that's the longest horizontal or vertical distance that we could hope to measure. So that horizontal leg is beyond our reach. The horizontal leg is a trick or a way around that is to use that 25-foot length and take another angle measure after we measure that far in towards the tower. So there Professor Mays is marching in towards the tower. The total distance of that tape measure laid out along the ground, that's 25 feet. And then after he has set up the transit at the new location, to set up the transit, there will be another sighting taken and another angle measured. This second sighting has an angle of 25 degrees as an angle of elevation to the top of that clock dial. So here's what it looks like with the extra information. It's the same vertical distance that we want to measure. The first position of the transit gives the triangle as it was with the single right triangle, but by moving the transit forward 25 feet, we have a second right triangle that we can build inside the first. Let me take this picture and draw it laid out in a little bit more of a formal sketch, the way you might see it or the way you might draw it to figure out the relationship among the variables. To figure out, this is the height h, the distance to the top of the clock dial that I've been wanting to calculate. That's the vertical distance. The horizontal distance is total length x plus y from the original transit location where we measured angle theta 1 to be 22.5 degrees. It's just y, an unknown distance from the second transit location where we measured angle theta 2 to be 25 degrees. So let's summarize the relationship among those variables with facts from right triangle trigonometry. First, the tangent of theta 1 is side opposite over side adjacent in that right triangle. Side opposite is h, and side adjacent is total length x plus y, as we've labeled things. For the other triangle, the triangle on the right, the angle there, theta 2, has side opposite h and side adjacent y. So tangent theta 2 is h over y. Notice in this set of equations that we have two variables, two things that I don't know. I don't know y and I don't know h. And three things that I do know. I did measure theta 1, theta 2, and x was 25 feet. That was the length of the ruler. So let's see how to take those two equations in the two unknowns, h and y, and rewrite them to eliminate the unknown that I don't particularly need, that's the value y, and solve for the value that I want to answer my original question to solve for h. Once I know h, I'll know the distance to the top of the clock dial. I'll know the distance So, we have tangent theta 1 is h over x plus y from the triangle in the picture before. Tangent theta 2 is h over y. Let's think about how to eliminate y. In that second equation, y is pretty much by itself in the denominator of a fraction. Let's solve the second equation for y. I'll multiply both sides by y and divide both sides by tangent theta 2. So that second equation is equivalent to y is h over tangent theta 2. Now, I will use that expression for y in the first equation. I'll just substitute in for it. So instead of writing tangent theta 1 is h over x plus y, I'll write h over x plus that expression. Tangent theta 1 then is h over x plus h over tangent theta 2. Well, I paid the price to get rid of y. Now I've got a complicated algebraic expression. I can make it a little bit nicer by simplifying that compound fraction. I'll multiply top and bottom by tangent theta 2. Then it gives tangent theta 1 is h tangent theta 2 over the quantity x tangent theta 2 plus h. I got that by multiplying the top of the equation on the right by tangent theta 2. That's so h times tangent theta 2. And the bottom by tangent theta 2. So the first term, x, has that tangent theta 2 as a factor stuck with it, and it cancels from the second term. Now let's cross multiply again. Tangent theta 1 times the expression on the bottom on the right, that is x tangent theta 2 plus h, is equal to just h tangent theta 2. So multiply it out. Tangent theta 1 times x tangent theta 2 is the first term on the left. Tangent theta 1 times h is the second term on the left. Now remember, we'd like to solve for h. What I really want is to know what h is. So I've got two terms involving h in that equation. I'll put them together by moving the h tangent theta 1 term from the left to the right. That is, I subtract h tangent theta 1 from both sides of that equation. Now I've got an expression on the right that I can factor h out of. Factoring h out and then dividing by that coefficient, it's h times the quantity tangent theta 2 minus tangent theta 1. Dividing by that, tangent theta 2 minus tangent theta 1, out comes an expression for h. All that's involved is, on the right-hand side, things that I know. X, theta 1, and theta 2. Theta 1. So what we have is a value for h in terms of x and theta 1 and theta 2. And we've also got values of those that we were able to directly measure. X was 25 feet, the distance that we moved the transit between the two sidings. Theta 1 was 22.5 degrees, and theta 2 was 25 degrees. So let's use those particular values to calculate what h is. Okay, let's use the Windows calculator to figure out how tall Woodburn Hall is. The formula that we had, we need to multiply x, which is 25, times the tangent of theta 1. Theta 1 was 22.5 degrees. Multiply that by tangent of theta 2, that's 25 degrees. That's what the numerator is. We want to divide that by the quantity tangent of theta 2, that's 25 degrees, minus the tangent of theta 1, 22.5 degrees. That's the denominator. Need a drum roll here. 92.69, let's call it 92.7 feet. That's how high the top of the clock is on Woodburn Tower, thanks to the power of trigonometry. Now I can't quite stop with the calculation that I had before. When you work through an applied problem, you have to make sure that you haven't let any assumptions sneak in that might affect the value that you report. What we wanted was the height of the clock tower, which would be measured from ground level. And all the measurements that we've done and all the triangles that we have used have been based on angles that we measured with the transit, angles like that. and the transit is measuring the angles at a convenient height to sight through the telescope, it's not at ground level. Everything is 5 feet up as far as the angles go, so that 22.7 degrees that we've measured is going to be relevant relative to the height of the transit. If we want the height of the top of the clock dial above ground level, we need to adjust by adding that missing 5 feet in. So a better value to report for the height wouldn't be 92.7 feet, but 97.7 feet. Don't forget the height of the transit.